Hi, today we'll be implementing a C++ program for a practical problem called horse race problem, leveraging the C++ function overloading, sorting, and implementation using dynamic programming. So here is the problem description that we want to solve. So the problem is the description is as follows. It's a racing league with a group of 20 horses where they all race against each other twice every year. So if the difference between two horses in the league table is greater than 4 positions, the winner of the race will be the one which is above the other in the table, as the other will not bother and will assume defeat. Otherwise, there will be a draw. So a person named Fred goes to bat. So he takes a folder with the league table and the multipliers for each race. So we have 20 horses. So and pair of horses has a multiplier associated with it. So a multiplier is a coefficient which is multiplied with the amount betted in case the prediction is failed. For example, if horse A and horse B race against each other and the multipliers are 1.1, uh, so if horse A wins, the multiplier is 1.1, 1.2 for draw, and 1.3 if horse B wins. So these are the betting amount that the Fred allotted for horses A and B when they are competing in the race, and the betting amount 1.1 when horse A wins, 1.2 if there is a draw, and 1.3 if horse B wins. So thus, if Fred bets 10 euros, then the multiplier for 1.1 when horse A wins will result into Fred winning or receiving 11. For when horse A wins, he will get 11, and if there is a draw, then he will receive 12, and 13 if he bets for B, then and B wins, and he will receive 0 if his prediction does not match the outcome. So the output criteria is this, that races are not at the same time, and if he earns money betting in one, he can bet this money in another race, as long as the second race does not start or occur at the same time. So there is and the races last for about 1 hour 30 minutes, and both the competition of the race doesn't there's no overlapping between, so he can bet in one race and then he can start betting on the next race. So assume all the races of a round start on the same day, with the start time between 1:30 p.m. to 23:59 up to midnight. So these are the exclusive time that the racing round can start, the competition can happen. So as there are 20 horses, there will be 10 races, and each horse will participate in exactly one. Would you be able to help Fred maximize his earnings that round? So I'd put the maximum combined multiplier he would be able to achieve by betting optimally. So the first we can analyze such a problem to maximize Fred's earnings. We can analyze the problem in key components. So first, understanding the race outcomes. If the difference between two horses in the league table is greater than 4 positions, then the higher ranked horse wins. So if there are a gap of 4 positions between two horses, so the higher ranked horse will obviously win, because the one in the lower rank will give up because there's already 4 position, one is already ahead of 4 positions. And if the difference is 4 or fewer, the race results in a draw. And betting strategy for each race is that like Fred can choose to bet on a win, higher ranked horse. So when he bet for the higher ranked horse, then he wins, obviously. A draw or a loss if he bets on a lower ranked horse. So we aim to select bets with the highest multipliers that match the most probable outcomes. And the betting cascade is since Fred can roll over his winnings from one race to the next, the sequence in which he places bets is important, because he aimed to maximize his betting return in an optimal order of races. So steps to solve the problem comprises those 4 steps. So first is data input and race analysis. So first we read and store the initial league table ranking. And then for each pair of horses in a race, we calculate the position difference to determine the most likely outcome. So if the difference between rank horse A and rank horse B is greater than 4, the higher ranked horse wins. Otherwise, the race is a draw. And the next is multiplier evaluation. For each race, consider the 3 possible outcomes: win, draw, and lose. Note the multiplier associated with each outcome: win, draw, or lose. And then select the outcome with the highest multiplier that aligns with the probable result. So we select the highest multiplier in between among the 3 possible outcomes: win, draw, and lose. So select the highest multiplier that aligns with the most probable outcome, probable result in that condition between the 2 horses, and there is a race in between. And if we saw then previously that if the difference between the pair of 2 horses is four positions, and then the higher ranked horse wins, and if it is less than 4, then the lower rank horse loses. So optimization using dynamic programming comes into play in the next step. So in this case, we use dynamic programming to maximize Fred's cumulative multiplier over all races in the round. So we use dynamic programming to maximize Fred's cumulative multiplier, and then we define dp variable as the maximum multiplier achievable by the end of the ith race. For each race, we assign an array or a position to be the maximum multiplier achievable for that particular race. And for each race, consider betting options and possible rollovers, updating that array positional variable dp accordingly. And then the next would be the output the maximum multiplier. Obviously, we will, after processing all races, we will output the maximum achievable multiplier, which will be the highest value in the dynamic dp table. So now let's implement this algorithm in C++. So here we have sections to fill. So first we have to implement the structure race, which is represents a single race storing the position of 2 horses, position 1, position 2, the start time, and the multipliers, multiplier horse 1, multiplier draw, and multiplier horse 2. So we have multipliers input for different outcomes. Then we constructor we need to implement the constructor initializes these values, and then we use overloaded operator, which compares race objects by their start time, enabling sorting by time, right? Because later we will sort the races structure in order of start time. So let's implement the structure for this. Struct race. So multiplier one, be then multiplier one, multiply two, then multiplier draw. So just name it as horse. The multiplier horse one, multiplier horse two. So we, because we have two horses associated, competing each other in and we are betting at least in one of the condition when one horse wins or the other one loses, or there is a draw. So we are initializing the variables multiplier horse one, multiplier horse one. We need to initialize that variable using so this is the position one, position two of the horse one, horse two, start time. Multiplier horse one would be so p1, p2, and then h g1 multiplier multiplier draw will be suppose past is as e, and then multiplier horse two is passed as g2, and then we initialize it. So this is like a constructor of the structure. So multiplier, make sure we are spelling it correctly. Multiplier draw. Yeah, we spell it correctly, but here is the needs to be the closing, and then yeah, raise yeah, then it looks good. So we initialize that, and then next we will do the overloading operator for comparing the start time for the race. overload comparator operate operator to sort races by start time. So if we have a list of races, we need to sort the races uh, in order of start time, and we need to compare that start time for each for each of the races, and we use our overloading operator in C++ to compare that start time for the race. Race 1, race 2, suppose we have two races, and then we compare them using in order of start time. So we return so race 1 dot start time is less than race 2 dot start time. So next will be the function to sort races, the sorts, which will sort the races vector by start time using the overloading operator that we implemented in the structure. So sort races uh, using the start time, not races. So we got vector. So we when passed as a list of races as a vector, we need to sort that vector. So sort races dot begin, and then races dot end. So we pass sort to the sort built-in sort function uh, the start of that vector and the end of the vector, and it will sort it comparing the start time. And then the next would be is the input table, which will read 20 horse names and assigns each a unique integer position in the in the horse to position map. This allows a quick lookup for each horse's position based on its name. So for each horse name, there is a unique position, um, integer position in that map. So we can quickly look it up based on its name, uh, and it will so we get the input the horse names, and then we assign positions for each of the horses. So this is the input table. In table. So now we assign the horse to position for the each of the horse name. So you get the horse name and assign sequentially inputted the horse names, and we assign linearly the position number for each of the horses. And the next will be the function for input races. So I previously already implemented it for such a function. Let's check it out. uh, Input horse names. Okay. Right now, yeah, we can do it for here anyway. So input races should be like this. So it will read race data, include horse names, horse 1, horse 2, the start time, the multipliers for each race, converts horse names to their positions using horse to position, and initializes each race object in the races vector. So let's do that. Input race. So let's avoid input races. Race. So we have this is the race structure, and we have a vector of them in that. So we call it races. And then map of that string, the string name to horse position in the map. For that we get horse address of horse to position to so then we get the string horse 1, horse 2, and then start time we get this as a string start, and then double multiplier 1, multiplier 2, and then another for the draw multiplier 3. So we have 20 horses for each of them. We populate the race structure. I less than, so we have uh, two pair of horses participate for compete for each other, compete with each other. So two horse uh, paired up, competing for each other, and we are comparing in between whether they have a 4 position difference in between them. So that we have 10 race entries, so two horses in a race, and then we will be having 10 races like this because two horses will be in a race. So 10 races will be as initialized as follows. So we get we need to get the one horse. The next will be horse 2, then start time, what is the start time of that race, and then the multiplier if it is one horse is if it's a winning multiplier, then draw or a loss. Now we initialize the races vector, races vector with the structure. So we have a vector of race structures. Um, so race. So we don't input position. We need to whether we need assign a position correspond for each corresponding horses. So horse to position. So raise horse to position I. So horse to position is horse to position horse 1, First for the horse 1, horse 2 position, horse 2, start time, multiplier 1, multiplier 2, multiplier 3, start time, and then the multiplier associated with it. So this concludes the input of the races. The next is the function multiplier. It calculates the multiplier for a race based on the position of the horses. If the horses' positions are within 4 places of each other, it returns multiplier draw. So if it is less or equal, uh, then it will return a multiplier draw. If position 1 is greater than position 2, it returns multiplier multiplier horse 2. Otherwise it returns multiplier horse 1. Right, so multiplier const race. So we get the race structure as an input, and we compare the position for that among that between the two horse. So if absolute we get p dot position 1 in that race, if one horse and then the next another horse, position 1 and position 2, so if the difference is less or equals to 4 horse positions, then our multiplier will be a draw. Return p dot multiplier draw. This is in the problem statement. And then else if position 1 is greater than period position 2, then we return multiplier of then we return multiplier horse 2. Otherwise it will be otherwise p dot position 1 is less than p dot position 2, and in that case we return p dot multiplier horse 1. So the next is the implementation for take away 1 hour 30, which is adjust a given start time by subtracting 1 hour and 30 minutes. It accounts for crossing the hour boundary. So if minutes integer is greater than or equal to 30, it simply subtract 30 minutes from it. Otherwise it adds 32 minutes and decreases the hour by 2. Returns the adjusted time as a string in minute format. Adjust start time by subtracting 1 hour and 30 minutes. Yes, we previously implemented such function. So this is mainly to adjust the start time by subtracting 1 hour and 30 minutes. So it's just for an adjustment of the with the of that one. So adjust a given start time by subtracting 1 hour and 30 minutes. Uh, so if we have a start time, we need to adjust that time by subtracting 1 hour and 30 minutes uh, because each race are of length 1 hour 30 minutes, and it accounts for crossing the hour boundary. If minutes integer is greater than or equal to 30, it simply subtract 30 from minutes, right? Because otherwise it adds 32 minutes and decrease the hour by 2, because to adjust it to make it for 1 hour 30 minutes long for each to be the race length, the duration for each of the race. Returns the adjusted time as a string in each hour and minute format. Yeah. And the next is the find best strategy. This is a dynamic programming implementation of finding the best strategy in our problem solving. Here it calculates the best betting strategy using dynamic programming, and we use DP factor based on the races multiplier. For each race for each of the race, we initialize DP variable with the race's calculated multiplier, checks all previous races J with a 1.5 hour window of I, and calculates the best strategy up to race I. So we have check all previous races J within a 1.5 hour window of I and calculates the best strategy up to that race. We need so dynamic program periodically adjust its variable DPI based on all previous races, and keeps track of the maximum achievable value by multiplying the current multiplier with the previous results in DP, and returns the maximum value at DP9. So it will at the 10th position of the variable the array DP, the DP9, which is the 10th position, and it will have the maximum value that is the maximum value of the multiplier that can be achievable, maximum achievable of all previous races, and find the best strategy for maximum combined multipliers. So let's implement that. So double find best strategy vector so we have a vector of races. So we are finding the best strategy among all the races, having returning the maximum achievable multiplier by the end of all races. So integer, and this will contain the races size. So now vector, we will have a double multiply table, dynamic DP table, and we have the races size. Then we initialize it with 1, so which is a neutral multiplier. 1.0 is a neutral multiplier. So DP array initialized to 1.0, which is a neutral multiplier. And then we go iterate through all the races less than n. So we have a current multiplier variable having multiplier, so we call the function multiplier, which will return the multiplier associated for a particular race. For ith race, we get the current multiplier, calling the multiplier function for that particular race. And then in the deep dynamic programming variable dpi, because dp variable stores the multiplier, and so currently we will only have the current multiplier as the multiplier. So current multiplier start with the current races multiplier. Calculate. Next we will calculate the latest possible start time for chaining previous races. So string max start time. So we get the maximum start time. So we will call that function take away 1 hour 30 races idle start time. Now, yeah, so for ith race, for that particular race, we have a start time, and we call take away 1 hour 30, so adjusted time, which will have the maximum start time. We will have a adjusted time returned for that particular race. Then we iterate over previous races to find the optimal chain. So we iterate over all previous races, j equals 0, j less than I. So we have starting from current race, and then we iterate over all previous races to the current race. So j equals 0, another variable j, it will iterate from 0 to I to the current race I, then j plus incremented, and then we compare if races j, if previous races one of the j start time, if its start time is less than equal to, if it is in the range of the current adjusted time of the race, if it's in the range less or equals to, it shouldn't be greater, it should be less or equals to maximum start time, which is the adjusted start time of the current race. We update the variable dpi max dpi, then our current compare it current dpi, we need to pick up the maximum one, dp j previous variable into current multiplier. So we update the current multiplier and times previous races multiplier, and then we pick the maximum of that. We just pick the maximum, so dpj it will yeah. So we have the betting amount and the current multiplier, and we pick the maximum of the current one and all the previous ones. we pick them, we skip the maximum multiplier in dp variable and ensure. So dp carries forward the maximum value up to raise I. So if I greater than 0, so dpi should be maximum, dpi. So we always need to make sure we are keeping the maximum of the carries forward the maximum value up to raise I. Um, then we need to just populate the main function here. So we call the input link table, which is the map. First is the string horse name to position, um, into to horse to position, then input table, which will it will input the table, horse to position. We pass the map into the input table, and it will populate the input table with the name to its position in the map. Mhm. And then we input the race data. So we have 10 race, and then we initialize the structure with some initial variables. Suppose we have 0 0, and then position 1 position 2, right? 0 0 is the initial, uh, and then start time 0 0, hour and minutes, and then multiplier, a neutral multiplier value as 1 for win, lose, and draw. So this is just the initialization of the races structure, the vector of races. Then we input races with races, and then horse to position. Then in the input races we so input races function will take races, that vector of race structures, and then horse to position. And then we need to, after we input the races, we need to sort it. Sort races, we sort it, we sorted the races, and then we calculate and we find the best strategy and output the result. So suppose cout in a fixed precision, set precision to 1 places in decimal, and then we call the find best strategy function. Then we pass the races as vector of race structures. Yeah. Okay. Right. So we need to check why our input races function name is not matching. It should let's check what was before here. Input table. Okay, yeah, that's why it was coming wrong. Yeah, spelled correctly now. Okay, so once we run the algorithm implementation, suppose, yeah, so here we can see that we first input 20 horse names. So here we input 20 horse names, and then we input the races, the horse 1, horse 2, the horse position, the horse 1, the name of the two horse involved in that race. So we have 10 races here, right? So we have 10 races, and then the start time, and then multiplier associated with it. So multiplier 1, multiplier 2, multiplier 3, 1.5, 2.0, 1.2. So one is the multiplier for winning, losing, and the draw. So we have 10 such races, and our dynamic DP variable updates the multiplier and give us the best or the maximum multiplier in all the in the races, comparing the sorting, the finding the best strategy and the maximum multiplier that will give the maximum outcome for the bet for betting that the person Fred can achieve. So after iterating for up to 10 races, our best multiplier, uh, the outcome, the result is 25.3. So this is the implementation that we wanted to discuss in this session, which using dynamic programming and our C++ sorting function overloading, uh, how we can use the techniques of C++ to implement and this problem. Thank you very much.